Welcome to a discussion of electron orbitals. Now, I'm assuming, might be a big assumption, that you watched the playlist Quantum Chemistry Fundamentals Spin, which is 14 videos. You can hop through them if you want, or you can just jump right into this topic. But this is a lot of times where studies of atomic electron behavior starts here. So I guess you can start here and then ask a bunch of questions to yourself. How does spin come in here? But I'm not going to go through all the details of spin. I'm going to make a lot of assumptions. Spin had very few dimensions. And remember, this is not a real space. When we talked about 3 electrons, well, it depends what you mean by a real space, but it doesn't have a 3-dimensional space that you normally think of in terms of X, Y, and Z. Instead, we had a 2-dimensional space with 1 electron and a 4-dimensional space with 2 electrons, and count them 8-dimensional space with 3 electrons. We didn't go any further than that. We went to hydrogen, helium, and lithium, and that's where we stopped doing all that. Now, with spin, we came up with allowed states. That means that they were allowed by the matrix algebra. What about the math that tells us where in the real space these electrons have effects? Now we'll find the electron isn't a ball. The electron really is a probability density. So it spreads out really throughout all space, but it has a much higher probability at one particular area. Not a point. It's not a point either. What determines that space? The determination is energy. The energy will take our spin states and determine which ones actually happen. And that's where we get a complete picture of what the electron is doing, its energy and its spin property. So if we have a special space that describes spin, then we have another space that describes these orbitals or position. For the spin, we determine the observables with spin operators. And as I said, energy has everything to do with where things are going to lie in the position. We have another operator called the Hamiltonian. And that Hamiltonian will take this infinite dimensional space of functions and not vectors. This infinite dimensional space has to be controlled with this Hamiltonian. That's not the best way to say it. Let's say that the Hamiltonian indicates what the positions that actually occur. So that Hamiltonian is very important. So if this information is interesting to you and you can see the transition from spin and spin operators to infinite dimensional Hilbert space and a Hamiltonian operator, then you're ready for the next video.